It's a great day to have a great day. Welcome back to the Boiler Wild podcast. My name is Eric Johnson. On this podcast, talk about boiler industry topics as well as personal development. The name WILD is a acronym that I came up with. It stands for work hard, invest in yourself, lead others, and develop yourself into a person of excellence. We should all strive to be better people in and outside of our career. Today is a wonderful sunny day back in the state of Florida, and I live in Tampa, Florida. It is a great, interesting city to live in, but yes, it is 95 degrees every single day in the month of July, and it is a great time to sit inside, record training, and record podcasts in the air conditioning. So that's what we're doing today. We are out here grinding, trying to change the landscape of training. I am attempting to make training for people in the boiler industry to actually move the needle. A lot of training is bite-sized training or entry-level training only, and it's more of a money maker or a side project to companies rather than the main thing. So I focus on training. I obsess over it, obsess over how people learn. I've learned a lot about how people learn and the ability of people to retain information is interesting, and how we retain it and what that actually means in a classroom setting or on the job training setting. And I think it's very interesting to look around and see what everybody else is doing, what's working, what's not working. There are tons of great companies out there that are providing training. There's also tons of training that's a waste of time and a waste of money. But that is a topic for another day. Today I want to talk about some hydronics. So the boiler purist will say a hydronic boiler or a hot water boiler is not a boiler. They'll say, oh, that's a cool water heater. But a boiler, while they may have started as steam only, and it's in the name, a boiler boils water, a hot water boiler or a hydronic boiler heats water, but it's not a water heater because it's not meant for potable use. There is a technical definition for a water heater, and there is a technical definition for a boiler, and they are not the same. So if you post a picture online, say on Facebook, and post it, somebody says that's a cute water heater, they're just putting you down because they have nothing better to do with their lives and they're miserable. So, hydronics. There are two main ways to pipe a hydronic system, and that's what we're going to talk about. We have primary, secondary, and we have primary variable. And I am going to discuss what those mean and hopefully describe it correctly. It's interesting to try to imagine, how do you describe the two without showing a diagram? Most people would throw up a diagram on a PowerPoint and they go, see, here's the water. This is how it moves. And, this is, you understand? Any questions? No? All right, let's move on. So let's start with primary variable. This is the on paper most efficient way to pipe a condensing boiler. You can pipe regular boilers this way, but they're normally not done. Primary variable. The condensing hot water market is the hot boilers to install, and the coldest return water gets returned to the boiler in primary variable, which supposedly increases the efficiency. Primary variable means that 100% of the water goes through the boilers. So what that means is if you have 3 boilers, so 3 boilers in parallel, 1, 2, 3, and we have a inlet and outlet. And think of these boilers, I like to call them refrigerator boilers. Most boilers that are condensing look like a refrigerator, only a little bit bigger. And so you got 3 refrigerator boilers, 1, 2, 3 in parallel. And you will have 3 inlets to those boilers, and you will have 1 header that goes into those inlets, and 100% of the system water flows through that header, and then will get split between the 3 boilers. And then on the outlets, you have 3 outlets on the boilers. The water flows out the outlets of the boilers, goes into a header, and then that header goes out to the system. And that is 100% of the water. There is no bypass. If you put a bypass in the boiler room, you're doing something wrong. The water that comes back into the return header is going to be the coldest, because hopefully we have removed all of the heat from the water that we can. You want a high delta T. A delta T is the temperature difference between the supply and return of the piping. So if you have supply piping leaving the boiler room, it may be 140 degrees. You're going to want your return piping as cold as possible while staying in within the limits of what the boilers can handle. Every boiler manufacturer will specify the delta T that their boilers can have and the flow rate that the boilers need to maintain. Some boiler manufacturers will tell you that they have no minimum flow rate through their heat exchanger, but there's still going to be that's just for damage, but there's still going to be a minimum flow rate through your system to maintain good mixing and a delta T that is acceptable. Otherwise, you will have heating issues throughout your space. So if we have 3 boilers, how do we control the flow through the boiler? So ASHRAE, which is I don't even know how to describe ASHRAE. It's a advocacy and regulatory group that's top dog for HVAC industry and more. But what does ASHRAE stand for? American Society of Heating, Refrigeration, and Air Conditioning Engineers. I knew that. I just couldn't think of that. So that's what ASHRAE is, but they set guidelines and standards, and there's this standard 90.1, I believe it's in, is it tells you can't have water flow through a boiler that's off. So if you only have 2 boilers that are firing, you'll have a boiler that's off, and you would have water flow through that. And due to draft, that water will be coming back, and it'll be hotter than the water in the boiler because you're not adding heat to the boiler. So that boiler is going to cool off, but the water is going to be hot, even though it's return water that's coming back through the boiler. And then with draft, you'll end up losing heat naturally as air is drafting over the heat exchanger and going up the stack. And it can add up to a lot of heat loss. And that's the reason why ASHRAE says you cannot have flow through a boiler that is not running. So on a primary variable system, we will have automatic isolation valves installed on each boiler. And those automatic isolation valves will either be controlled by the boiler, which is, I believe, most common because it's just easier, or the call for heat on the boiler. So if the boiler is off, the boiler will post-purge and keep the valve open for, say, 15 seconds after there was a fire in the boiler, and that's going to help get the remaining heat out of the boiler, and then it's going to close the isolation valve. The isolation valve is normally going to be like a butterfly type valve. That's going to be a sealing butterfly. This is going to be a different type valve than like a gas butterfly valve that's used for like firing rate control. It's going to be a sealing type butterfly valve, and it's going to be on a slow closing actuator. So 15, maybe 30 seconds to close the valve, depending on how large the valve is. It's not going to be like a solenoid that just snaps open and close. Boiler turns off, valve closes, and now you've isolated flow from that boiler. And now all the flow that would have gone through that boiler is now split between the two boilers that are still running. Now, if another boiler turns off, goes into post-purge, 15 seconds. That boiler will close the isolation valve. And now you have two boilers that are off that have no flow. And 100% of the water is now going through the first boiler, or the boiler that's running. And it is the only boiler adding heat to the system. And then you might say, where are the pumps? That's an excellent question. So on a primary variable, we have a, how do I say this? You have one required pump for the entire system. Since the flow is forced through the boilers and the boilers are part of the main loop on primary variable, you don't need a boiler pump for the boilers. You just need a system pump that will pump the water from the pump outlet all the way through the system, comes around back through the return into the boiler room, and then it comes through the return side of the boilers. The boilers heat up the water, and the water goes out and then goes into the inlet of the pumps and keeps going on its way and keeps doing that over and over and over again. Normally, you'll have pumps in parallel, so when you see more than one pump and they're installed next to each other, that's, I would say, 99% of the time it's going to be pumps in parallel. I don't believe in hydronic heating systems you'll ever see a pump in series. I'm sure there's a reason for it, but I haven't seen it. Pumps act different if they're in series versus parallel. So parallel pumping, same thing as parallel boilers. You will install the pumps next to each other, and depending on the pump being on or off, the water will go through the pumps equally. So you'll have an inlet header, and it could either go through pump 1 or pump 2. And those pumps will get designed to pump water throughout the entire system and through all the boilers. There's a cool thing called pump head that essentially the engineer looks at the longest pressure drop throughout the piping. So in order to pump water, piping has friction, and that friction is resistance to flow, and a pump has to overcome that. So you look at your longest circuit and you make sure that you can do that, and then you go back and balance the building and balance your flow rates based on what you need for all your coils. But one pump can handle the entire system. Very often, though, you'll have two pumps. One will be a backup. If both pumps are running and they're in parallel, they don't need to be. You'll be better off if you just run one pump. You're probably wasting energy if you're running two pumps in parallel, or your pumps are not sized correctly. So one pump, boilers, pump, flows, system piping all the way through the system and all the way through the boilers. Boilers have automatic isolation valves. The isolation valves close when the boilers are not firing, and then they automatically open when the boiler goes to fire. So when a boiler has pre-purge or a call for heat, the valve will open, and that'll start pushing water flow through the boiler. The boiler will light and then start heating that water. I guess I should cover it. The main way to control the firing rate of boilers in a primary variable system will be for one header sensor. So all the boilers will work together to achieve a header temperature, which is the most preferred way. So say we're firing all three boilers, they're gonna, instead of modulating based off of their internal water temperature, they're gonna modulate based off of their header temperature. So you'll have most boilers manufacturers, they'll have their own internal control system that can communicate with multiple boilers. So the boilers can communicate with each other. The header temperature sensor, which will be downstream of the outlet header of all the boilers. So if you have the outlet header, you'll have each boiler connect into it. And then after the last connection, as you're traveling out to the system, you'll have your header temperature sensor. And that will take the average of all the water that is in the header for the boilers. That header temperature water is the temperature of the water that is heading out to the system. So that is why each boiler is modulating to achieve that water temperature instead of the internal water temperature of the boiler. If you have your flow rate, if your flow rates are off or not balanced correctly between your boilers, you may have a boiler that runs a little bit hotter, and it will, if each boiler was modulating to its own temperature, it may cycle, even though it may cycle on set point and say, hey, I achieved set point before the system has actually achieved water set point, and now the boiler would turn off and then it would cool rapidly and then it would turn back on. And you would have a lot of hysteresis when you are trying to achieve set point of the system. One header temperature sensor, all the boilers in parallel will work together to achieve the temperature of the header. Each boiler typically will have a firing rate that matches the other boilers. You're going to want to fire your boilers in parallel. And this goes back to having all the boilers connected together. Typically, these days, the boiler manufacturer will have the ability to connect all the boilers together so that they can see each other. But the boilers will modulate together. So if you have three boilers, they may all be at 30% firing rate. Header temperature isn't where it needs to be, and now we're going to increase our firing rate to 35% across all three boilers. That's how primary variable works. We have 100% flow through all the boilers. We have isolation valves, and we have one pump for the entire system. All the redundant pumps, if you have like a pump that is a spare, that's a spare pump. Running both pumps does not make your system better. Opposite of that, I hope I described that correctly. It's weird. If you've never tried to teach somebody verbally without showing pictures, so many things in the boiler world are supported with pictures, although I think there is an art to describing things, but I wouldn't say I am far from an expert on describing things, but that's why I'm doing this. That's why I'm trying to get better. So hopefully that makes sense. And hopefully I kind of map that out in your mind if you don't already know. But the biggest indicator of primary variable is going to be that you see automatic isolation valves on the boiler instead of pumps. And that's where we'll get into primary secondary. So primary secondary is the tried and true method of pumping. This is what most older buildings were done as. It involves two separate hydronic loops. I'm not going to try to get into too much of how pumps work, but essentially you have to disconnect pumps from each other, if the pumps can like see each other, and by see, like if you have water flow that is interfering between two pumps, now you have a system that is designed wrong and the pumps won't work correctly. So how you avoid that is you have how the name sounds. You have a primary loop and you have a secondary loop. And I believe technically the secondary loop is the boiler loop and the primary loop is the system loop. And think about two loops of water, so two circles, or let's say two rectangles, because most piping isn't circular, but two rectangles, and only on one edge do they touch each other. And the secondary loop that is in the boiler room is going to connect into the primary loop at two connections. You always need two connections with water. You have an inlet and an outlet. And typically, this is done with closely spaced T's. And when you have a closely spaced T, you have minimal pressure drop between the 2 points, and it allows flow in between the two loops without interfering with each other. That's as basic as I can make it. And you will see, if you open up a manual, you will see closely spaced T's. That is intentional. The T's should be as close as possible together. The water flow will interact between those two T's, but it'll allow the secondary loop and the primary loop pumps to act independently. And another way to do that is to have a hydraulic separator, which is a large tank. This is typically not done on a commercial system, as it's an added cost that, to be honest, I don't know if a hydraulic separator is better than closely spaced T's. I know it's going to cost way more, but I don't know if it's better. Closely spaced T's work well, and the hydraulic separators, I know the benefits of it and how it works, but I can't tell you if there are benefits over closely spaced T's and why a commercial building would use it and spend the cost. Like depending on your system, a hydraulic separator, you can get into 4-inch, 6-inch piping, and all of a sudden you're paying 10 grand for a piece of equipment that could be optimized with closely spaced T's, and it takes a lot less space. So if you know specifically why a hydraulic separator would be used in a commercial system over a closely spaced T's, email me or DM me on LinkedIn. I would love to know. But the hydraulic separator is just another way to separate the pump loops from each other and allow the water to interact and mix between the two loops, but the pumps do not see each other and therefore are not affected by each other's pumping. But we'll go with closely spaced T's. So these closely spaced T's, like I said, the water will mix between the two loops, but the pumps will not see each other and will not be affected by each other. I think that's as simple as I can say it. I'm not going to go into how the water flows between closely spaced T's. At a surface level, you just have to know they just have to be as close as possible together. And that typically with piping, that's like 4-inch piping, you'll have them 1 to 3 feet apart, which is fine. But if you make them 10 feet or 20 feet, now you have pressure drop in between the T's, and you will start having issues. So closely spaced T's, look in your manual. That is intentional. That is a primary indicator of primary secondary. So opposite of primary variable, primary secondary. So we have two loops, and we have a secondary loop, which is in the boiler room. We have a primary loop, which is going to be our building loop or our like load. And that primary loop will have one pump. It may have more pumps in parallel, but it has one required pump. And then in the secondary loop, we will have a pump per boiler. So we'll keep the same example. We'll have 3 boilers, and off the back of the boiler, somewhere on the inlet or the outlet, it depends. I know some people want pumping away from the boiler. Some manufacturers don't care. But somewhere on the inlet or outlet of each boiler, you will have a pump. And that is the key indicator for a primary secondary system that is installed correctly. I'll get to a story on why that's not always true. But installed correctly is the key indicator. And for review, once again, primary variable is going to be a automatic isolation valve on the boiler. On the inlet or the outlet, it doesn't matter. And on the primary secondary system, on each boiler, it's going to be a pump. So the pumps are what force the water through the boiler and move the water out to the closely spaced tees. The water mixes and will carry the heat out to the primary loop, which is the system loop. And that will go out to your load, to your rooms, to your air handler coils, whatever. That water will cool down. It will come back around in the loop, and that water can mix at the closely spaced tees, and cooler water can now get transferred into the primary or into the secondary loop, which is the boiler room, and will go back through the boilers, and it will be forced through the boilers by the pumps. If you turn off a pump on a boiler on the inlet or outlet, you will stop flow through the boiler, and therefore you don't need an automatic isolation valve. So that still applies to ASHRAE 90.1, I believe it is, of you do not want flow through a boiler that's off, but it will naturally not flow because you no longer have a pump running. And all the boilers are going to be in parallel. So once again, they'll all be next to each other, and they'll all tack on. I don't even know how to how do you describe parallel? Think of like a ladder, and you have rungs, and here we go. You have an extension ladder, and you have rungs, and each boiler is a rung. So you can have 20 rungs on an extension ladder, and if you say, hey, we have too many rungs, let's cut it down in half, and you cut off 10 rungs, now you'll have 10 rungs left, and each rung being a boiler, the system capacity will just be cut in half. That is what parallel is. In series, it would be each boiler lined up next to each other in the sense that you have the inlet to the boiler, and then the outlet of the boiler goes to the inlet of the next boiler, and then the outlet of that boiler goes to the inlet of the next boiler. And I do not believe very many boilers, if any, are ever installed in series. I don't know why a boiler would be installed in series, but I'm sure there's an application. I never say never. I'm sure there's an application, but 95+% of boilers are going to be installed in parallel on a hydronic system. Each boiler will have a pump. That pump turns on. When that boiler fires, that boiler heats that water gets pushed out into the header of the secondary loop. That secondary loop water will run around and go through those closely spaced tees, which will mix with the primary loop and carry that water out to the building. I think that's as simple as I can describe primary secondary piping. I hope I described that correctly, but the key is pumps on the boilers, and primary variable is isolation valves on the boilers, And one giant system loop and primary variable is one small boiler loop and a larger building system loop. And let me tell you a story about that. So I was starting up some condensing hot water boilers, and you go in there, and on a startup, you walk into a mechanical room that you've probably never seen before. You typically don't review anything. You're not involved with the design process or anything. So you walk in and you have to take in the piping and the install, and then you'll have the mechanical maybe have their foreman like lead you around, and they'll say like, "Yep, does this look good? Like everything's good. Like we're ready to go. Like, can you start this up?" And you kind of just have to, you got to get your bearings. So I was walking into this mechanical room. There's 3 boilers, and I know the boilers very well. They're very robust boilers, and I'm looking at it, and I'm like, huh, this is kind of weird. So then I'm like tracing piping, and I'm like looking at it, and I'm like, the system piping seems to be set up for primary variable. I'm like, I don't see any closely spaced T's. I don't see like 2 loops. Like, what am I looking at here? And what confused me was each boiler had a boiler pump. And in a primary variable, as you've recently learned, I should be looking for automatic isolation valves. So I note it, and I'm like, man, I must be dumb or seeing something here, because why are there boiler pumps on a system that is primary variable when I should only have a system pump? And I have 2 system pumps over on the side of the room. Only one needs to run, and those system pumps will modulate the water flow in the system based on delta P, which I won't get into, but it modulates the water flow based on the demand of heating load for the building. And I asked the mechanical to look at the drawings. I'm like, yep, it's a primary variable system. So why do we have boiler pumps? So I do everything else. I tell them whatever else is wrong. This needs to be here. This needs to be here. The header sensor was too far down in this case. So on the last outlet of the boiler, we had about 40 feet of piping. And then they had the header sensor, which was just closest to a master panel. And it would save on wiring, I guess. But now that that's 40 feet of piping, that adds lag to the system, and we want that header sensor closest to the last outlet, after the last outlet of the last boiler that is making the water head out to the rest of the system. So, hey, we got to move the header sensor, do this, do that. And I make a note like, hey, I'm just a lowly service tech, but the boilers have pumps on them, and I don't understand why. And we send that off. I give it to my manager. Manager gives it to the mechanical sends it to the engineer. The engineer comes back and says, hey, that's correct. I designed the boilers to have pumps so that they are like turbo pumps and will help water flow throughout the boiler. And if you don't already know, you cannot tell an engineer that they are wrong if you are not another engineer. And even if you are another engineer, it's very hard. And I'm just a lowly service field person on a job that this engineer hasn't even seen. Engineer is 10 states away. I can't even talk to him in person. Mechanical can't even talk to him in person. And I'm like, that doesn't make sense. Whatever, I'll start it up. And I start up the system, and all we do is have flow issues. And each boiler pump had a VFD, and there were so many wires because now my master panel had to control all those VFDs and those pumps instead of just the boilers controlling an isolation valve. And I had to lead the low voltage contractor through how to wire all that. I'm like, this is ridiculous. And started up, and shockingly enough, the water flow throughout the system didn't work too great, and the pumps didn't work too great. And no matter the speed that I ran the boiler pumps, the boilers would not stay firing, and they would just constantly chip off on water temperature. And how you need to think of water is like a chain in a pipe. So think of water as a chain. And on primary variable, we have one large system. So you'll have one giant chain that goes throughout the entire system. And you'll have a pump, which is, think of like a gear that moves that chain. So as you know, if you pull on a chain, you're going to move that chain. But then if you push on a chain, it may bunch up on itself. However, since the chain is one giant chain, it ends up being a loop where you can pull on the chain, and as you know, your force of pulling is the same force that is going to be moving the chain in the direction that you are pulling. So the chain will move throughout the system, no problem, just like a chain would move on a bicycle. You move the gear, and the chain goes round and round and round. Now, add in a second pump on that main chain, and now spin that pump and try to make that chain go faster, even though all the lengths have to stay the same. So think of a bicycle, and you are pedaling on your bike, and you have that one chain going around your two sprockets, and now somebody else comes in and adds in another sprocket that is in between the two, and they are going to pedal faster than you are pedaling. What do you think is going to happen? Everything's going to bind up. Now think of that chain, that one giant chain going throughout the system. You have your pump, which is your gear, moving that chain, and the chain is just traveling in a loop all the way through the system. And now you have on the opposite side of that, say on the opposite side of that pump of the system, you add another pump, which we'll think of as a gear. You connect it to the chain, and now you try to spin that gear twice as fast as the original gear that is moving the chain initially. So either the gear is going to break, or you're going to break the chain, because you cannot move a chain that is connected continuously throughout one loop. You cannot move it faster in one spot and also slower in another spot while maintaining the same amount of lengths and the same spacing. That would, it breaks all physics of how to do that. So that's essentially how water works. But water is different than a chain in that you can just cavitate a pump. It doesn't matter that the pump is running, it just won't move water. And that's essentially what is happening. So when this engineer was installing pumps to turbocharge the water through each boiler, you have this giant chain throughout this entire system of this water, and you can't just speed up water that is connected together on the same chain. And surprisingly enough, the pumps didn't do anything. And after a series of very many phone calls and meetings and way too much time wasted, the engineer finally agreed that we shouldn't have pumps and that a hybrid primary variable, primary secondary system was not a good idea. And we should just go to the tried and true primary variable system and install isolation valves. So we install isolation valves, and after another unrelated series of water flow issues where the balancer balanced the building wrong, and they finally fixed that. That was a whole nother debacle in itself. But after those issues were fixed, the boilers had never ran better, and the entire building heated itself how it was engineered to. And now there were 3 brand new pumps, or I would say gently used pumps, sitting next to the boilers with VFDs on the walls that were shut off, with control wiring, 3 sets of control wiring to each VFD that's no longer needed. And we just installed isolation valves on each boiler, and it works. Imagine that. I don't know what was going through the engineer's mind when they thought they could install a hybrid system and that you could turbocharge water like that. But that, think of water as a chain, and that's what I'm kind of talking about when the pumps see each other. So why you don't have that same thing with primary secondary is primary secondary has 2 chains of water. You have a chain of water in your primary loop, which is going to be your main building loop with all your loads, and your secondary loop, which is going to be your boiler loop. And the 2 chains are moving past each other, but they're not the same chain, and they're moving in opposite directions. And those 2 chains, by moving past each other, pick up heat and transfer heat between each other, in this case, the water, but they do not actually move together and are not powered by the same gear, which are the pumps. And that's how you got to think about how pumps move water through a system. If you put pumps in series, those pumps will hydraulically see each other, and now they're all connected to the same chain of water, and each pump will affect how that water moves. But you can't just spin a pump at twice the speed and speed up the water and then slow it down because all the water is connected together essentially as a chain. So there is a reason to put pumps together in series. So series pumping will double the pressure, I believe, if I'm remembering. It's been a bit since I went over how pump laws and that. I learned all that in college, which was 9 years ago at this point, which is crazy to think about. But I have yet to see series pumping on a hydronic system. You will always see parallel. So parallel will be flow. You change the flow with parallel, you change the pressure with series. So that's primary, secondary, primary variable. If you are unsure, the number 1 indicator is you look in the boiler room, and if you see a boiler pump, so a pump very closely connected to each boiler, 95% of the time that is going to be a primary secondary system. In this case, I'll back up. 100% of the time that is going to be a primary secondary system. But if it's a new system, don't be surprised if something's installed wrong. It shouldn't happen, but it happens, like the story I just told, where you have boiler pumps for a primary variable system. So walk in the boiler room, you see boiler pumps, you're going to have primary, secondary. You walk into the boiler room, you see automatic isolation valves, you're going to have primary variable. Hopefully I described that correctly. Primary variable has 1 giant loop of water. All the water has to flow through the boilers. Primary, secondary, you have 2 loops. You have a smaller loop, which is the boiler loop that provides and adds heat to the water. And you have the primary loop, which is the larger loop, and that is your building loop, which will remove heat from the water on all your loads. And they mix together at a closely spaced tees or a hydraulic separator. Hopefully I described all that. Hopefully all that makes sense. If you have any questions on that, if you want to learn more, manufacturers' manuals are great to learn. They all go over how to connect a hydronic boiler, either in primary, secondary, or primary variable, and like where to put your valves, where to put your balancing valves, where to put the pumps. They normally have a great diagram. Open up the manuals, use manuals. You'll be smarter if you use a manual. You can stumble your way through a lot of problems just by reading the manual and referring to the manual. You don't have to memorize the manual, but being able to pull up a manual and refer to it is a superpower, and it seems so easy, but so many people don't do it, and you will be better than, I would say, 80%, even higher, but 80% is conservative. 80% of people, when solving problems in the boiler industry, if you can pull up the manual. And how I do that, or used to do that, I mean, I still do it, but I'm not fixing boilers every day. But how I recommend to the people I teach and anybody I talk to is to maintain a cloud system of manuals. The days of having to carry around boxes and boxes of manuals are gone. Have a cloud system of all your manuals, and you can pull it up on your phone, you can pull it up on your tablet, and organize those manuals how that makes sense to you. Download them, put them in the cloud system. And now when you have a question, you can just quickly access the manual on your phone, pull it up, you can search the manual, look at a diagram, say like, yep, that's wrong, yep, that's right, all right, that's what I thought. Maybe you're checking an igniter gap for a burner. You don't have to memorize that information. You just have to know that it exists and where to find it. And when you have your own cloud system, it is easy to find information instead of constantly re-downloading the same manual from the manufacturer's site. So get a cloud system. If you work at a company with other people, I would hopefully at this point you'll have a cloud system that you share between everybody, and everybody can add manuals to the cloud system. Now you have to keep it organized and name everything in a way that makes sense, but everybody works off the same set of manuals, and you now have no excuse for not being able to find the manual because it's on the cloud system that you can access with your phone or your tablet. That's what I recommend. Use the manual. You'll be better. Everybody says, read the manual, all that stuff. That's my number one thing. That's what helped me best in my career, is reading the manual. If you also want to read a textbook about pumping, Dan Holohan has, if you are unaware, Dan Holohan is probably the number one author for boiler books. He has since retired, I believe last year. He'll do maybe an article a year, I think I've seen, but he used to write normal articles. His daughter runs heatinghelp.com. That is a great forum and website to learn from other people, to post questions. But Dan Holohan has some great books on steam systems and hydronic systems, and you can go look it up. Just look up Dan Holohan. All of his books are on heatinghelp.com. I'm sure you can all find them on Amazon, but all the list of books are on heatinghelp.com. If you have any questions or anything else, you can DM me on LinkedIn. You can email me, eric.johnson@boilearn.com. That's ERIC period JOHNSON at BOILEARN.com. I appreciate you listening. If you enjoyed this episode, please rate it 5 stars. 5 stars for everybody. I am doing my best, trying to get better, trying to bring some value with every single episode. Let me know if you learned something too. DM me on LinkedIn. If you're not on LinkedIn already, get on LinkedIn. get a profile picture, interact, DM me that you listened. I would appreciate it. Thank you for listening, and stay wild.